How's it going? Let me just set this window up so we're ready to get going here. I hope everyone can hear me. Let me know if you're having any trouble. And we'll take a couple minutes just to get going. Hey, Kara, how's it going? Great to see some familiar folks here. Let me just make sure we're all get this mic a little bit closer here. Dude, we've missed you. I've missed you. I missed all of you. This is so much fun for me to do. And yeah, I just, I know it sounds kind of sappy, but I just really appreciate that I have the opportunity to do this, right? I love helping people learn stuff. I love helping people get ready for this test. I love talking about science. I love teaching people science. So it's like the fact that this can be my job, thing that I do, is just super cool. It's super, super cool. So today we're going to talk about diffusion and osmosis. And diffusion and osmosis are very important topics for the TEAS. They show up in the chemistry section. They show up in the life science section. They show up in the anatomy and physiology section. So it's like knowing about diffusion and osmosis are going to give you a big boost across the science section, okay? Not just in one section, but across the science section. Okay, so before we get going, as some of you know, I like to wait a minute or two for other folks to join. And we're gonna, it's kind of like you go to a Pixar movie and they have a little short at the beginning where they talk about something else, and then we'll get to the main event. So, what I want to talk about here, real quick, is two things. I got a delightfully hateful comment the other day on one of my videos, and this person said, "I hate your videos. You say the same thing a bunch of times in different ways. Just say it once and move on." Well, you know what? I hate your comment. Look, guilty as charged. I do say the same thing a bunch of times in different ways. I do that intentionally. Like, that's what I'm trying to do. So look, if you don't like my videos, don't watch them. But I'm trying to do that. And here's why. I'm not trying to waste anybody's time. I don't want to waste anybody's time. Have you ever seen a little kid learn something? I bet a lot of folks out there, you have kids, you've watched them learn language, right? Think about teaching your little kid how to talk. How many times do you have to like hold up, a pen? You're like, this is a pen. And then, they forget it. What's that? It's like, this is a pen. This is a pen. This is a pen, right? You say it over and over and over again, and then they get it, right? And then it sticks in their mind eventually. But, the way we learn science, the way we learn anything is not that different. It's really actually identical to like how a 2-year-old or a 3-year-old learns language. We have to hear the same thing over and over again. And that's how it sticks in your mind. So it's like, yes, absolutely. To this comment, I'm sorry they hate my videos, but I do try to say the same thing a bunch of different times so that it sticks in your mind so that you don't forget it. You hear something once, you're never going to remember. Like, you're just not, right? You're not going to remember it if you hear it just once. So that's why I say it a couple different times. And as this person correctly pointed out, I said a bunch of times in different ways. I never just repeat myself and repeat myself and repeat. I always say things in different ways so that it, because everybody learns differently. So there are different things that will stick in your mind. So I just want to say that I'm not, I'm not trying to annoy anybody. But I am trying to help you learn. So that's why I'm doing this. Okay. I might repeat things a bunch of different times. I might say things, but a couple different times. There's one thing that I am not going to do. And that is, I am not going to read definitions at you. I'm not going to read jargon definitions. And I'm mentioning this because somebody the other day sent me an email and they said there were not enough definitions in my videos. And I said, well, a lot of other YouTubers, they teach me the definitions. Look, it's not this person's fault, but I just want to say definitions filled with jargon technical words do not help you for the TEAS. Okay, right? We're going to be talking about osmosis today. I'm going to break down osmosis into simple terms. I'm going to use simple words. It's going to be like I'm explaining to a 5-year-old because that is how we all learn. Okay? I know there are other YouTubers out there. I know there are other books out there. This is how they would describe osmosis. Okay? And you would not learn anything. Maybe you'd feel good that you were hearing a definition, but you are not going to learn it. Here's what they'd say. They'd say, Osmosis is the net passive transmembrane flux of a solvent across a semipermeable partition. The movement is driven by a difference in chemical potential between a region of low solute concentration and a region of high solute concentration. And then they'd move right on to the next thing. They'd say, now, diffusion is the movement of substances. That is not how people learn. You do not learn by having somebody read technical definitions at you. And this is one of the reasons why, I'm always a little bit spicy. And I say, people come to me and they say, I'm never going to be able to pass the TEAS. I'm never going to be able to get a good score. And they tell me the resources they've been using. And it's like, bro, it's not your fault, right? The videos you're watching are garbage. The books that you're reading are garbage. It's not your fault, right? If your videos sound like this, you're not going to learn anything. If your books sound like this, you're not going to learn anything, all right? So I really want to show folks that if they think they can't do it, probably the problem's not you. The problem is the videos, the books, the resources that are just not good at teaching, okay? So I'm going to repeat the same thing a bunch of times so it sticks in your mind. I'm not going to use technical jargon like this. So just wanted to get that out of the way. Love me or hate me. You can turn the live stream off right now. Nobody's making you watch it, right? Just saying, for the people who like the way I teach, I try to meet you where you are and take you step by step through this. Okay, so we got a bunch of people here on the chat. Let's get going. Today, we're going to be talking about diffusion osmosis. As you know, I love to hear from people. If I can help you out, send me an email. Tyler@teasandoneday.com. Boom. I've got a whole bunch of resources, including a full chemistry course, teasandoneday.com. Check it out. You can put your email in there too if you want to get notifications of every time I do a live stream. teasandoneday.com. Just sign up. You can get some free chemistry stuff. I'm not going to spam you all the time. Just put your email in there and I'll let you know when I'm going to do a live stream. Okay, so as I said, for the folks who got in here right at the beginning, diffusion osmosis are special topics on the TEAS because they show up in 3 science sections. They show up in the chemistry, they show up in the life science, they show up in anatomy and physiology. These concepts are important across many areas of science. If you learn this stuff, you get a big boost throughout the science section in many different areas. Now, I want to start this video in a little bit of a different way because I don't want to waste anybody's time. I do not want to waste anybody's time. So what I want to do is I want to help you figure out, like right now, do you need to learn this stuff? What we're going to do is we're going to do 2 practice questions. And if you get the practice questions right, honestly, I mean, I always love it when people stay in the live stream and they contribute and they have fun. If this is fun for you, that's great. But if you get these 2 questions right, honestly, you're pretty good at diffusion osmosis. And you're probably not going to learn a whole bunch from this video. You might get some review. That's fine. But if you can get these questions right, you're in pretty good shape. Now, if you don't get these questions right, if you hear the questions and you're like, I have no idea what he's talking about, this is total gibberish, don't worry about it because by the end of this live stream, it will make sense. Got it? Do you need to learn this stuff? Question number 1. Let's see. Okay, I'll read it, give you a sec to think about it, and then we'll do the answer. Do you need to learn this stuff? Well, let's find out. Which of the following is true of passive transport? It is movement of a substance from an area of low concentration to an area of high concentration. B, it is a process that typically requires energy. C, it involves a chemical change that makes a substance more soluble. Or D, it can involve either solutes or solvent. Okay, think about it for a sec. And the correct answer is... The correct answer is D. It can involve either solute or solvent. Okay, number 2. Let's take a look at this. What is the correct description of how osmosis functions during water reabsorption in the kidney? A, energy is expended to pump water back into the blood from the tubules. B, water moves from the tubules, high solute concentration to the blood, low solute concentration. C, water moves from the tubules, high water concentration, to the blood, low water concentration. Or Water moves against its concentration gradient as it moves from the tubules to the blood. Think about it for a sec. I gotta check on my my pencil here. I'll be right back. All right, give me 1 second. I gotta like plug this in so that it pairs with the whole, you know, iPad. It's being difficult for me. Give me just 1 sec. Plug this guy in. There we go. Boom. Okay. Plug this guy back in here. Should be everything that we needed. Go back here. Perfect. Switching to USB. Looking good. Okay, sorry about that. Sorry about that. The correct description of how osmosis functions during water reabsorption in the kidney C. Water moves from the tubules, which have a high water concentration, to the blood, which has a low water concentration. So people are feeling pretty good about this. Some folks are a little bit confused, but people are feeling good about this. So you just think about it. You know, if you want to stick around, that's awesome. You know, if you're feeling good about this, you just want to watch the video for review. That's great. If this is stuff that you're feeling a little bit shaky about, don't worry. By the end of this video, it's going to be super, super clear. I'm changing all this sort of stuff up. I've moved a bunch of stuff around this weekend because I'm doing some like renovations in this attic room. I forgot to turn the lights off. Let me turn the lights off. Boom. There we go. Now I'm not getting the like reflection off my my iPad. Okay. Finally. It's like, is this guy ever get started? We're finally ready to go. Let's get going. We are going to be talking about diffusion and osmosis today. If you got any questions, let's just like throw them into the chat. All right. Okay. So today we're going to be talking about diffusion and osmosis. And at oh, let's get some light on. Ooh, that's so much better. That looks good. It's like, yeah, that's nice. Get a little color in the skin too. I don't look like quite such a corpse this way. So diffusion and osmosis are, at the end of the day, these are ways that substances move from one place to another, and that they often use diffusion and osmosis to cross barriers. Okay. And we know lots of examples of diffusion and osmosis in everyday life, in anatomy and physiology, if we think about them. Okay. So, for example, you probably know that in the lungs, we have, in this diagram, you can see we got the person with the lungs, we got the zoom in on the capillaries and the alveoli, and then in here, we know that oxygen moves from the lungs to the blood, right? And we know that carbon dioxide moves out of the blood into the lungs. That is an example of diffusion. Those are both examples of diffusion. We have substances that are moving from one place to another, and they're crossing barriers. Okay. Now, another example of osmosis and diffusion is water moving in and out of blood cells. This is something that you run into a lot in anatomy and physiology classes. You learn stuff like this. Here in the middle, in this beaker right here, we have a red blood cell. Okay. And if you take that red blood cell and you put it into pure water, what happens is that lots of water moves into it. Water moves into it, and it swells up. Okay. Water in. If you take a red blood cell like that and you put it in really salty water, water comes out. So that is also an example of how substances are moving from one place to another. They're crossing the barriers. They're crossing the barriers of the cell. So think about like oxygen, carbon dioxide moving in and out of blood and lungs. We've got water moving in and out of red blood cells. This is the kind of stuff that we're going to be talking about. Okay. I wanted to put some ideas in your mind so you know where we're going. Okay. Let's start at the very beginning, okay? Diffusion. That's where we're going to start. Diffusion is a fancy term for spreading out. And you know a lot about diffusion from your daily lives. Things in nature naturally spread out. We have two examples on this slide right here. Okay. First, I bet everyone has experienced this. You have somebody who is in a restaurant. They're in a bar, they're whatever. They're on the other side of the room and they pull out a cigarette. They light up and they start smoking. And what is eventually going to happen to that smoke? That smoke is eventually going to spread out into the rest of the room, the whole bar. You got some guy over in the corner smoking a cigarette. Just a minute or two, you're going to be able to smell that smoke in the whole bar. And the reason is diffusion. That smoke doesn't just stay in one place, it spreads out over the whole bar. Perfect example of diffusion. Another example of diffusion, I love doing this. I love doing this like when I'm cooking. I love doing this with like if I'm ever teaching kids because it's so fun, it's so easy, right? That's what we got down here. We got a beaker of water, glass of water. You put a drop of food coloring in. What happens to that food coloring? It doesn't stay in one place, right? It spreads out. The food coloring naturally spreads out until eventually we get to the end here. We get the beaker or the glass, and the food coloring has spread out through the entire thing, right? So whether it's smoke or whether it's food coloring, stuff like that, things like to spread out. And that, at the end of the day, is what diffusion is all about. Now, sometimes people say, okay, why does diffusion happen? There's a very simple rule, and that's that whenever they can, substances will spread from an area where they have a high concentration to an area where they have a low concentration, and they're going to try to even out on their own. Things in nature try to even out on their own. And let me show you what I mean by that. Okay, here we got this dude, okay, and he's smoking, right? So our definition says substances will spread from high concentration to low concentration on their own. Now, concentration might sound a little fancy, but all we're talking about really is the amount in a certain area, certain volume, certain place. So let's think about this dude's cigarette, right? So right now, we have when he first lights up, okay, he first lights up, you can see we got a little cloud of smoke right near him. And so that means that starting out, we have a high smoke concentration right, close to his face where the puffs of smoke are. But over here, we have a low smoke concentration. We might have no smoke concentration, okay? And the point is, we have an area close to his face where the puffs of smoke are, high amount of smoke, high concentration of smoke. Further out, low concentration of smoke. And so what nature tells us is that over time, often doesn't take very long, the areas where we have high concentration of smoke are going to spread out to the areas where we have low concentration of smoke. And eventually, we're going to end up in this situation over here where, the smoke has kind of spread out everywhere. It's evened out everywhere in the bar. All right? It's not just going to stay high close to his face, very low elsewhere. It's going to go from high to low. And it's going to try to even out. Okay? This is a fundamental rule of nature, that things go from high concentration to low concentration and they try to even out. You will never, right? And this happens on its own. You just sit there smoking your cigarette, smoke spreads out from high concentration to low concentration. You will never see the opposite thing happen, right? That's what I mean when I say this is a rule of the universe. Imagine somebody smoking, right? Smoky bar. You will never in this universe see a smoky bar get less and less and less smoky and get all the smoke focused around some dude's cigarette, right? Things never spread out in reverse, right? Things never go from a smoky bar and all the smoke concentrates and focuses on the dude's cigarette, right? One happens on its own. The other never happens. Isn't that crazy? And just think about that, right? That you never see that. You never see a smoky bar never unsmokes itself, right? And focuses on the dude's cigarette, right? Okay, so the exact same thing is happening when we put food coloring in water, right? So it's like we start over here. When we put the drop in, right, we have a high concentration right there where the drop is. How about food coloring elsewhere in the glass in the beaker? We have a low concentration. Well, if nature has its way, things aren't going to stay like that. We're going to get diffusion. Things are going to spread out. This coloring is going to spread out from the high concentration to the low concentration. We can see that happening here. It's starting to spread out until eventually it is spread all the way out and now it's evened out. So diffusion happens because things, whenever they can, want to spread from high concentration to low concentration. We saw this in two examples here. The dude with the smoke spreads out in the bar, the food coloring spreads out in the glass. High concentration to low concentration. It happens on its own. It does not need outside energy. Just smoke just spreads out. Food coloring just spreads out whenever it has a chance. Okay. Any questions about this? Now, I gave you these two examples because they're easy to see, they're easy to think about. They're examples that I'm sure all of you have experienced, like in everyday life, like you know how this works, okay? Now I want to take this stuff that you know from everyday life and I want to start applying it to things that happen in the body, things that happen with cells that are not quite so easy to picture, but now that you have a background, it'll be easier to kind of like understand what's going on, even if we don't visually see it or visually experience it like on a day-to-day basis. And that is that, as you know from anatomy and physiology, oxygen diffuses into the blood. Maybe you didn't know that the word was diffuse, but you know that it moves into the blood. Okay, so what we see here in this diagram is we're zooming in. We have a picture of a dude with their lungs, and then we have the alveoli and the capillaries, and now finally this is, oh no, I don't want to do that. And then finally we have one alveolus, if you want to call it that, which is that one of these tiny little lung sort of sacs of lung tissue that's surrounded by a kind of capillary. Now, oxygen goes into the blood. And here's why, because in the lungs, you take a deep breath in, there is in the lung area, in this alveolus, there is a high level of O2, a high concentration of O2. And in the blood, there is a low concentration of oxygen. So, what does the oxygen do? The oxygen naturally, without using energy, diffuses. Oxygen is able to pass through the cells and it's able to pass into the blood. It is diffusing. Because it can pass through the cells, it can pass into the blood. It's going on its own from an area of high oxygen concentration to an area of low oxygen concentration. That's why it moves in to the blood from the lungs. Okay. Now, you also know, or you might also know, you probably know, that carbon dioxide in the lungs comes out of the blood, it goes into the lungs, and then we're able to breathe it out. And that's because the opposite is happening, right? We have, initially in the lungs, we have a low CO2 or carbon dioxide concentration. We have in the blood, we have a high carbon dioxide or CO2 concentration. What do things always want to do whenever they're given the chance? They want to even out their concentrations. So if we have a high amount of CO2 in the blood, it is going to want to move, shoop, 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 shoop out of the blood. It's able to cross those cells. It's able to cross through them, move from the area of high concentration in the blood to an area of low concentration in the lungs, gets out of the blood, we can breathe it out. Okay? High concentration to low concentration, moving, we call that diffusion. Okay, let me take a look at the chat here. Am I jumping ahead if I ask about the ocean? in like a high salt concentration, for example, dropping stuff into that, for example. I don't entirely know what you're asking. So if you give me a little bit more information, I would be happy to answer that question. I'm just not sure exactly um what you mean. So give me a little more information. We'll get back to that. As I keep saying, diffusion happens without added energy. It just happens on its own. The dude smoking the bar diffuses from high concentration to low concentration. It spreads out through the bar without adding any extra energy. The food coloring spreads out, diffuses through the glass without adding extra energy. It just happens on its own. And because of that, we call this passive transport. Transport means moving something, right? Transportation is moving something. It's trucks, it's boats, it's planes. Transportation is moving. And passive means that it just happens, right? We don't have to put a lot of energy into doing it, it just happens. So, passive transport, it happens without added energy. Two other examples that we just saw in the lungs: passive transport, oxygen from the lungs into the blood. Passive. It just happens. You don't need to add extra energy. Passive transport, carbon dioxide diffuses out of the blood into the lungs. Passive transport. It just happens on its own. Cigarette smoke, spreading out through a bar. Passive transport. It just happens on its own. All right? You don't have to put in any extra energy. Okay, let me take a look at the chat here. Saw concentration when you drop the ink. I don't want to say oil because that's really thick blood. Is that changing the whole spectrum that we're talking about here? Blood, is that changing the whole spectrum? Concentration. I'm going to say oil. It's really thick. I'm so sorry. I just still don't quite know what you're asking here. You say you try to keep your question short. Write as much as you want. To give me as much information, write a paragraph if you want. No big deal. Write a paragraph, and I'll figure out what you're helping with, what I can help you with. Okay. So just to do a quick review of this, right? Let's look at this example. We have blood flow through tissues. We have a capillary here. This image that you see is a capillary. Okay, and a capillary is a very thin blood vessel that usually is about one red blood cell thick. Okay, so what can we say about the concentrations of oxygen and carbon dioxide? Because we know that two things happen. Okay, and that's a little big. I don't love that. I wanted to go big, but not that big. We know that in the tissues, usually oxygen comes out of the blood and carbon dioxide goes into the blood. And so, what can we say about the concentrations of oxygen and carbon dioxide in the blood and in the tissues? Well, if oxygen is coming out of the blood and it's going into the tissues, we must have a high oxygen concentration in the blood. We must have a low oxygen concentration in the tissues. So that's why it is moving, diffusing from high to low. If carbon dioxide is moving from the cells, from the tissue into the blood, it must be a high amount of CO2, a high concentration of CO2 in the tissues, and a low amount of CO2 in the blood. And that's why the blood is getting the CO2, right? So in both cases, we're moving from high concentration to low concentration. This is diffusion. It's passive transport. It's happening without any added energy because the oxygen and the carbon dioxide can pass through the walls, the barriers, the membranes of the cells. They can move in and out of the blood. Oxygen is going to move from high concentration to low concentration. Carbon dioxide is going to move the other way. in the other direction, but it too will be moving from an area of high concentration to an area of low concentration. Let me know if you got any questions. Let me know if I can help with anything. Okay, so what we're going to do now, is we are going to shift gears a little bit. We've been talking about things at a large scale. Okay, we've been talking about smoke, and we've been talking about food coloring, and we've been talking about, lungs and blood and tissue. Okay, now what I want to do is I want to like pretend that we go like kashoop. Okay, we're going to zoom in on individual cells, and we're going to use some little diagrams. Very simple diagrams, but they're important, right? You might see diagrams like this in the TEAS. You're probably going to see them in tech. You're definitely going to see them in the textbooks for anatomy and physiology. And we want to be able to understand these diagrams and how things move. Okay, so there are a few things that you will want to know about these diagrams. Okay, the first is you can see it's a very simple representation of a cell. Okay, I'm just doing an oval. Okay, but that's supposed to be a cell. And the line around that cell, well, that's my cell membrane, right? The cell membrane, remember, it's like this sort of saran wrap, a layer that surrounds a cell. What I always like to say about the cell membrane is it keeps the insides in and it keeps the outsides out. That's why a cell has a cell membrane. Inside in, outside out. Now, these little dots, what are these little dots? These little dots are things that are dissolved in the cell or in the area around the cell. This is dissolved stuff. Maybe it's salt, maybe it's sugar, maybe it's a gas like oxygen or carbon dioxide or nitrogen, right? It's just whatever it's a substance that we're interested in. Okay, salt, sugar, oxygen, carbon dioxide, some sort of a waste like urea, maybe it's an amino acid. It's just whatever we're interested in. These are some of the things that can move in and can move out of cells. Okay, so let's take a look at a few different examples of how substances would move in and out of cells when they're given the chance. Boom. Take a look at this cell. We have this substance, these little green circles. These are a substance. Let's say that it's I don't know, it doesn't matter. Let's say it's a waste. Okay, it's like bacterial pee. Okay, whatever. Let's imagine it's a bacterium, or it doesn't even matter. It's just whatever. It's something the cell wants to get rid of. Now, think about this. As you can see up here, it says the substance can pass through the cell membrane. Okay, that's important. The substance, this little green circle, can pass through the cell membrane. So, what is going to happen if we just let the cell sit there? What is going to happen? Well, we have differences in concentration, right? Look, inside the cell, outside the cell. Inside the cell, we have a high concentration of these little green dots. Outside the cell, we have a low concentration of these little green dots. So, what is going to happen? Since the substance can pass through the cell membrane, over time, these little green dots are going to move out of the cell. They're going to pass through the cell membrane. They're going to try to even out from high concentration to low concentration. And eventually, we're going to end up with a situation kind of like this that we see here, right? Because these green dots are moving from high to low, high to low, high to low. And then we end up in the situation that we have over here on the right, where everything's kind of spread out, you know? These green dots pass through the cell membrane. They diffuse from high concentration to low concentration. And remember, how do they do it? They do it on their own with no added energy. Passive transport. Passive transport because it's high concentration over here to low concentration. Boom. High concentration to low concentration. Passive transport happens on its own. Spreading out. It's all about spreading out. What about this situation? Here we have some red triangles. We check it up here. This substance can pass through the cell membrane. Okay, we have a situation that looks like this. Over time, what is going to happen? What's going to happen? Well, first, do we have some different concentrations? Yes. Outside the cell, there is a high concentration of red triangles. Inside the cell, we have a low concentration of red triangles. What happens with passive transport, with diffusion? These things move from high to low. So many of these little triangles are going to move through the cell membrane into the cell. And boom, we're going to end up in a situation like this because we went from high to low and we increased the amount of red triangles that are inside the cell. Okay, diffusion, high to low concentration, and assuming this thing can pass through the membrane, passive transport, it happens on its own. This stuff is going to move through the membrane all on its own. Now, the next thing we're going to talk about is called facilitated diffusion. Facilitated diffusion is a little bit of a special version of diffusion. And facilitated diffusion is what we get when something can't pass through the cell membrane, but it can pass through special little channels or tunnels instead. So look at the example that we have here. We have these blue squares. Now, the information that we have about this situation is a little bit different, right? It says this substance cannot pass through the cell membrane. Okay, but it can pass through these special channels. And they look like little gray, I'm drawing them as little gray cylinders, right? And often in the membrane of a cell, we will see little channels or little tunnels, and things can pass through them. Okay, so take a look at this. Boom, I added some in. So now we have this situation where we have blue squares. They can't normally pass through the cell membrane, but they can move through these tunnels. So now what's going to happen? Think about it. Same thing. I'm sounding like a broken record, which is kind of the goal, so that this ends up sticking your head like glue. We have high concentration of blue squares inside the cell, low concentration of blue squares outside of the cell. What are these blue squares going to do? They are going to move out of the cell if they can, and they're going to have to pass through these special channels, but that's how they're going to get out. They're going to get out by moving through the channels. They're going to diffuse from low to high. And the reason why this is called facilitated diffusion is because to facilitate means to help something. Okay? These substances can't pass through the membrane on their own, but they want to get out, so they pass through the channels instead. They pass through the channels instead. And that's all facilitated diffusion is. Facilitated diffusion, as I say here, as long as a cell helps a substance cross the membrane with tunnels or channels, the diffusion process happens on its own. So just like regular diffusion, it just can't pass through the membrane, but it can pass through the channels, it can pass through the tunnels. So this happens without any extra energy, just like other forms of diffusion. It's a type of passive transport. It's a type of passive transport. You have to have the channels, you have to have the tunnels so the stuff can get out. But as long as you have those, the stuff moves through the tunnels on their own. Yeah, the glucose, salts, ions, things like that have been mentioned. They're examples of things that sometimes have to pass through channels or tunnels in order to get into or out of a cell. What's going to happen in this case? We have these little green triangles. Well, again, they can't pass through the cell membrane, but they can pass through the special channels. So we have a high concentration on the outside, low concentration on the inside. The net movement is going to be into the cell through those little channels. And again, this is an example of facilitated diffusion because you have these special channels. It happens on its own, high to low concentration, and it doesn't need extra energy, which means it is an example of passive transport. Any questions about this? Let's bring it on. We have seen a variety of examples of things that will happen on their own and do not need any extra energy. And things that are going to happen on their own are going to be situations where things move from a concentration that is high to a concentration that is low. So I'm drawing them in right now. Boom, 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 boom. On the left here, we have high concentration inside the cell. Going to move out. What I've tried to do on the right, maybe I said right, I meant left. You know what I meant. Over here on the right, we have a high concentration of the little dots outside of the cell. They're going to move in. Okay. Sometimes if the dots, the stuff that we're talking about, can't pass through the membrane, we're going to have some little special channels to let them pass through. That's then facilitated diffusion. But the idea is all of this happens on its own. Maybe the stuff can move high to low through the membrane. Maybe it can move high to low through a channel or a tunnel. But either way, it's moving from high to low. It's happening on its own without extra energy. Example of passive transport. Any questions? Great. Now, I keep saying it happens on its own without extra energy. It happens on its own. It happens on passive transport. It happens on its own. It happens on its own. You're probably so sick of me saying this, and that's good because it means it's beginning to stick in your head. Okay, but here's the thing: are there any examples where where it doesn't happen on its own? Yes. Look at this. We have these little yellow hexagons here. Imagine this is a nutrient. Imagine this is something that the cell wants to bring inside. Okay, take a look at this. Imagine this is something that the cell wants to bring inside. Think about it. Can you see a problem here? Okay, let me tell you what the problem is, or the challenge. The problem is currently we have a high concentration inside the cell, and we have a low concentration outside of the cell. That means that if left to their own devices, these things want to come out. That would be the normal direction of flow on their own. We'll say that would come out. They would come out on their own. But the cell doesn't want that, you see. This is a nutrient. This is sugar. This is something like that. And the cell wants to bring it inside. That's a problem. Because if these little things are left on their own, they are going to move from high to low concentration. They're going to float out of the cell. The cell doesn't want that. It wants to bring more in. What's it going to do? How can it do that? On their own, they move from high to low. They're going to float out of the cell. So what the cell has to do is the cell has to pump them. It has to pump them, pump in with energy. And once again, that's because they would move from high to low out of the cell on their own. And so if the cell wants to get more of them inside, it must use energy to pump them in, to pull them in. And we call this an example of active transport. Passive transport, they would diffuse out on their own from high to low. Active transport pumps them in from low to high. They don't want to go in that direction. They want to spread out. They want to go from high to low. But the cell says, I'm sorry, you can't do that. I'm going to pull you in. And in order to do that, in order to do the opposite of what they want to do, the cell has to use energy. It has to do active transport to pull them in against what they want to do. They want to go from high to low. The cell must use energy to get them to do the opposite. Here's another example. Let's imagine this is a waste product here. Okay? This is a waste product. Now, normally, what would happen is we have a high concentration outside the cell. We have a low concentration inside the cell. Without energy, on their own, they would move in this direction. They would move into the cell. And I'll say on their own. On their own, these things would move from the high concentration outside of the cell into the cell. But the cell doesn't want that because this is a waste. This is like urea, this is pee, this is whatever. It wants to get rid of it. And that's a problem because on its own, this stuff is going to come in. It's going to be going from high to low on its own. What are we going to do? How's the cell going to do? How is the cell going to get the stuff out? Because it wants to come in on its own. It's going to have to pump it. It's going to it's got to turn on the pump. It's got to use energy to pump it out in the direction that it doesn't want to go. Boom. We're going to use red. Boom, 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 boom. This one. Sorry, I know you don't want to go in this direction. I know you want to go from high to low, but pump it out. Pump out with energy. You got to spend energy doing this. Again, active transport. When you want to make things, substances, go in a direction that they don't want to go, you got to use energy, right? You got to push them out. You got to push them out. Active transport. Pump them out. Pump them out. That's how you're going to do it. You're going to use active transport. Things go from high to low on their own. If you need something to go from low to high, you got to pump it. That's going to take energy. It's going to be active transport. Okay. So we're about halfway through. Let's review what we've talked about, and then we're going to go on to osmosis. Just some examples here to make sure that you know what we're talking about. Diffusion or passive transport. Okay. That is where we have high to low, and the thing diffuses out without using any energy. It does it on its own. You need energy if you want to take something with a low concentration and bring it into an area with high concentration. Things naturally move from high to low. They don't go from low to high. So to go all the way back to my earlier example with the guy smoking a cigarette in the bar, I said that the smoke is going to naturally spread out from high concentration to low concentration on its own. Okay? You could imagine a situation where you could collect all that smoke and concentrate it back into a very small area. But you would have to use energy to do it. You'd have to get fans. You'd have to get machines with filters. You got to plug a bunch of stuff in. You could collect all that smoke and pump it into a very small area, but you would need to use energy for it. And that's the point. Things spread out on their own. Passive transport doesn't need energy. Things do not collect on their own. They need energy. Things go from high to low concentration on their own to spread out. Things do not go from low to high. You got to pump them. And you can think about the same thing with water, right? It's instead of talking about concentration, we're talking about height. But it's like if you have water at a high level, it's always going to flow like a waterfall or something. It's always going to flow from high to low. It does that on its own. You don't have to pump a waterfall. Waterfall just works. But if you have water that's low, you got to pump it up to get it high. Similar idea here. Okay. Active transport. You have a low concentration outside. You have a high concentration inside. You got to pump the stuff in. Okay. And the last thing that we can do here is we can introduce two more terms you might see. When something goes from high concentration to low concentration, we can say that it is moving along the concentration gradient. Concentration gradient, you don't have to worry about all that stuff. It's kind of, jargony. Just means along the concentration gradient is high to low. It's the direction that it wants to go. Okay? However, if you have something at a low concentration and you want to go to high, that takes energy, as we said, and you have to move it against the concentration gradient. And that's a term that we use, against the concentration gradient. Okay. Let's do a couple quick examples. Here we have a cell. We have some yellow triangles. Which the stuff can move in two directions. It can go into the cell or it can move out of the cell. Which direction will require energy and which direction will happen on its own? So let's think about this. Which is going to require energy? Think about that. You can put your answers in the chat. Is it going to be into the cell or out of the cell? What is going to require energy? Into the cell or out of the cell? Into the cell or out of the cell? So think about this. We have a low concentration in here. We have a high concentration here. Maybe I should have asked first, what will happen on its... Oh, look, I can't even write sometimes. On its own is what I meant to say. What's going to happen on its own? Let's start there. Let's not worry about that. What is going to happen on its own? The stuff is going to move from a high concentration to a low. Here, I'll color code this. Green. Green. On its own is going to move in like this. No energy. It's going to naturally move from high to low. That's going to be passive transport. Passive transport on its own, moving from high to low. What is going to require energy? Active transport. What is going to require energy? It's going to go in the opposite direction. And it's going to mean that we're taking this thing at a low concentration and we're pumping it out to go from low to high. So into the cell is going to happen on its own because it's going from high concentration to low concentration. Pumping it out, getting it out of the cell is going to require energy. That's going to be active transport because going from low to high. Okay, let's look at another example. Okay, here we go. Let's think about this just like I did before. Which is going to happen on its own, which direction, and why, and then which is going to require energy. And remember, this is going to be passive transport, and the energy is going to be active. The first thing you always want to consider in questions like this is you want to think, where is the high concentration, where is a low concentration? I'm going to spend a minute on sort of color coding this while you think about what's going to happen. On its own, which direction is it going to go? Which direction is going to require energy? Okay. Okay, so first, on its own, let's think about this. How do our concentrations work out? High concentration inside the cell, low concentration outside of the cell. So on its own, this stuff is going to want to move from high to low concentration. It's going to move out of the cell on its own. Okay? Move out of the cell on its own. What is going to require energy? It's going to require energy to do the opposite. It is going to require energy to get it into the cell. I should have drawn it through the channel here. It is going to require energy to go in. So to sum this up, out, it will leave the cell on its own. It will need energy to get it in. And that's going to be an active transport process. Okay. Any questions about this? I'm going to tell you right now, we're gonna shift gears. We're gonna shift gears, and we're gonna talk osmosis after I have a drink of water. After I fix my hair, we're gonna talk osmosis in just a sec. Any questions at all that I can't answer? This is going to be posted up on YouTube. So if you got to go, you got to go. I know we're reaching kind of the hour mark. If you got to go, it'll be posted as soon as we're done. You'll be able to find it on YouTube. It'll like start uploading. And then I think tomorrow or Thursday, we'll do a bunch of TEAS practice questions on this. We're not going to do them today because like getting through osmosis is going to take, I don't know, maybe 30 minutes, 40 minutes. So, I mean, this is going to be kind of a long live stream, but this is important stuff. And I want to make sure that we kind of go, step by step. So, yeah, just real quick. Yeah, Rhonda put something important in here, and that's that she mentioned the term ATP. ATP is a substance that the cell uses for energy. So that's something you might want to keep in mind. Maybe that's something I should have mentioned. ATP is something that the cell uses for energy. Anyway, so sometimes I'm like, what would require ATP? Well, something that would require ATP would be something that requires energy. Yeah. So I think tomorrow or Thursday we'll talk. We'll do the TEAS practice questions, and then the next live stream I'm going to do is going to be on microbiology. It's going to be the microbiology, like specific for the TEAS, what you need for that. And so for microbiology, what you need for the TEAS is you got to know a little bit about the different types of microbes. Well, look, at a high level, microbiology is like tiny little living things. Okay. So you need to know about that are called microbes. And so you need to know about the different types of microbes. Okay. So like bacteria and fungi and protozoa, stuff like that. And then you gotta know a little bit about the different types and viruses too. You got to know kind of how they work, the similarities and differences between them. We're going to cover that. Then you got to know a little bit about the microscopes, different types of microscopes that a medical professional or a scientist might use in order to see them. And then, the biggest thing that you need to know for the TEAS when it comes to microbiology is you need to be familiar with a bunch of common diseases. And you got to know what kind of microbe they're caused by. You got to know if they are transmissible, if they can be transferred from one person to another. And yeah, basically that's what you got to know. And the TEAS, the ATI book doesn't focus on that very much, but the ATI questions do. So it's one of those things like if you just read the ATI book, you wouldn't know that's something you need to focus on. But the actual test questions are like super heavy lean into like, mumps. Is that a bacteria, a virus, a protozoan, or a fungi? Right? And it's like you wouldn't know to study that based on the ATI book, but you got to know it. Just as usual, the ATI, as I always say, there is a lot of stuff on the TEAS that is not in the ATI book, and there's a lot in the ATI book that is not on the TEAS. I don't know why it drives me nuts, but it's true. So when we talk micro, we're going to spend a lot of time focusing on that stuff, like common diseases. What are they caused by? What type of microbe are they caused by? Or are they not caused by a microbe at all, right? There's some things that genetic disorders, diabetes, cancer, Down syndrome, they're not caused by microbes at all. And you got to know that too. So when we talk microbes, we'll talk about all of those different categories. Anyway, when is micro? Micro will be end of this week or beginning of next week, I would say. So let's move on here. Now we're going to talk about osmosis, which is diffusion of water. At a very high level, that's what osmosis is. It is previously We've been talking about other types of stuff. Now we're going to be talking about diffusion of water, right? As we said just here, this is examples of sometimes water goes into cells, sometimes water comes out of cells. Osmosis is movement or diffusion of water. Okay, so up until now, we've looked at diffusion like this. We've been looking at maybe gases, oxygen or carbon dioxide going in and out of blood. We've been looking at stuff like maybe it's sugars or salts going in and out of cells. But we haven't really been talking about water. Water can move too. Salt can move, sugar can move. Maybe I got to pump it, maybe it moves on its own. But we haven't really been talking about water. And there's a thing here, we've been drawing diagrams like this, which are perfectly fine. It's the way they show up in textbooks, it's the way they might show up on the TEAS. But the thing is, there's something we're not showing here, and we got to remind ourselves what it is. And what is it that we're not showing here? When we see the cell, we see the cell membrane, we have these little dots and stuff like that that represent something that's, sugar or salt or something. What are we not showing? Boom, we're not showing water, right? All of this is happening in water, right? Cells are filled with water. Cells usually live in environments that are filled with water, right? So like your body is filled with water. There's water everywhere. So there's water inside cells and there's water outside cells. And when we start talking about osmosis, we got to remember that all of this is happening in water, right? So there is water inside the cell. There's water outside the cell. And that water in osmosis might move, out of the cell. It might move in the cell. But you got to remember there's water absolutely everywhere. These little dots, as we said, represent stuff that's dissolved in water. Maybe it's sugar, maybe it's salt, maybe it's amino acids, maybe it's waste, whatever. Stuff dissolved in water. We've got water in the cell, water outside of the cell, and we've got stuff dissolved in it. Now, there are some important terms that we need to use. Now, I've avoided using the jargon up until now. They're kind of like jargon alert, right? I've avoided using any jargon because we didn't need to know it. But now that we're diving a little more into osmosis, we do need to know it. So there's just a couple terms that we need to know because they're going to show up on the TEAS. And there are better ways to describe the stuff that is dissolved and the water, right? The dissolved substances, we call them the solute. And the water, we call that the solvent, okay? Dissolved stuff, sugars, salts, solute, water is the solvent. An important thing to remember here is that a solute dissolves in a solvent to make a solution. So let's think about this, right? Let's imagine we have a glass of water here, and we have some salt. Here's some salt. Here's my little pile of salt. We have water. We have salt. And what we're going to do is we're going to put a little bit of the salt, we're going to dissolve it in the water. Okay? What is the solute? What is a solvent? What's a solution? Well, a solute dissolves in a solvent to make a solution. So the salt is the solute. The water is the solvent. And the thing that we end up with after it all mixes together is a solution. Now, if any of you are watching my TEAS chemistry course, you'll know I talk a lot about this. Solute, solvent, solution is important in chemistry. It's also important with this osmosis and diffusion stuff that shows up all over the place. But solute, solvent, solution is particularly important in chemistry. If any of you have been watching that course, I have the stupidest way to remember this. You'll never forget it, but it's so freaking dumb, okay? It's so stupid. So imagine that like a pirate, okay, has a bag of loot. And they have this bag of loot and they're like people are chasing them or whatever. And they take the loot and they hide it in a vent. This is my vent. It's a really bad vent. They hide the loot in the vent. Solute dissolves in solvent. Isn't that dumb? But you'll never forget it. The pirate hides the loot in the vent. Solute dissolves in solvent. So the salt is the solute. The water is a solvent. Boom. You'll never forget it. Loot goes in the vent. So once again, water is a solvent. Dissolved substances are the solute. So oxygen dissolves in water. It could be a solute. Salt dissolves in water. It could be a solute. Sugar dissolves in water. It could be a solute. Many different types of solute. Water is a solvent. When we're talking about living things, we're talking about cells, water is a solvent. Okay, so now we are ready. We are ready to talk about the most important thing that's going on here in osmosis. When does osmosis happen? Osmosis happens when solute can't leave the cell. So water moves the other way instead. Let me say that again, because it's like big shift. Osmosis happens when solute can't leave the cell. So water moves the other way instead. Look at this. We have a cell with these red dots. There's an important note in the lower right-hand corner. It says this solute can't pass through the membrane. Many solutes can't pass through the membrane of cells, and they don't have special tunnels or channels that let them through. So the solute wants to do this. The solute wants to come out, but it can't. It can't do it. It can't get out, right? Because we have high here for the solvent. We get solute. We have low solute outside. The solute wants to get out of the cell, but it can't. It can't pass through. So what happens instead? Water moves in. The solute wants to go out. Water moves the other way. Water goes in. Water. Let me say that once again. Solute wants to move out. High to low. High solute concentration inside the cell, low solute concentration outside. Solute wants to go from high to low. It can't pass through the membrane. It's like, let me out, let me out, let me out. Membrane's like, no way, you can't pass through. And the solute is like, but there's so many of us in here, and there's so few of us out there. We want to go from high concentration to low concentration. And the membrane is like, you are not coming out. You're not passing through. So water moves in. Water moves in the opposite direction, and that is osmosis, the movement of water. In the chat, what does not dissolve in water? Many things do not dissolve in water. Things that are oily, fatty, do not dissolve in water. Lipids do not dissolve in water. And we can talk a lot about that. I talk all about that in my chemistry course. But I just want to make an important point here. When I'm talking about this stuff, I'm not talking about what doesn't dissolve in water. The solute that wants to get out of the cells, it does dissolve in water. It just can't pass through the membrane. Sand, right? Sand does not dissolve in water. Metal does not dissolve in water. Like metal, like little metal dust does not dissolve in water. There's lots and lots of things that do not dissolve in water. Wax does not dissolve in water. Gasoline does not dissolve in water. Anyway, when does osmosis happen? You have a solute that can't leave the cell, so water moves the other way instead. Let's look at another example. Okay, this solute, this little pentagon here, can't pass through the membrane. What does it want to do? Okay, what does it want to do? What does it want to do? It wants to, the solute wants to go in. Solute wants to move in from high to low, but it can't pass through the membrane. It wants to go in. So for osmosis, whoop, the water goes out instead. Solute can't go in. Water can't go out. So an excellent question was just asked in the chat. And the question is, why can't solute go out in what situation? We're going to talk about that right now, and then we're going to come back to osmosis. This might be confusing when I talk about solute can't go in, solute can't go out. because we just spent a lot of time talking about how carbon dioxide and oxygen move in and out of cells. We talked about diagrams like this where we have salts and sugars and stuff like that that pass through the cell membrane, or they pass through special channels. We looked at lots of examples of solute being able to pass through a cell membrane in and out of it. But the thing is, examples like this are special situations. You got to learn about them because they are important. It's important for cells to get nutrients in. It's important for cells to get waste out. It's important for oxygen and carbon dioxide to move in and out of cells. But they are special situations. They're actually not the norm. The norm is most solutes in a cell and in living things can't pass through cell membranes. Most of the stuff that's in a cell can't get out. There's proteins, there's DNA, there's RNA, there's amino acids, there's just like thousands of things, all this crap inside of a cell, and only a tiny amount of it can get out. Most of the solute inside cells cannot come out. And that's something that people don't understand. And the reason why, like, osmosis is really tricky. But one of the reasons that osmosis is so tricky is that nobody says that. Nobody says this fundamental thing that's like most solutes in a cell are stuck inside. They can't get out. Now, why can't they get out? At the end of the day, the simple reason is most of them are too big. Only tiny things can pass through a cell membrane. Most solutes are just too big to get out. Others have too much of a charge. They're ions, and it's very hard for them to move in and out. But at the end of the day, most things in a cell, most solutes in a cell just can't frickin' get out. They're too big. They can't pass through the membrane, and there do not exist channels or tunnels that allow them out. So what you got to do is to really understand osmosis. You got to imagine that the cell is filled with lots of solute that can't get out. And when we talk about situations like stuff easily diffusing into and out of a cell, it's important, but that's not the norm. Now, the other thing to keep in mind is that there is a lot of stuff outside cells that can't get in. There's stuff in blood that can't easily diffuse in cells. And like in the lab, I can put cells in solutions that contain a lot of solute, and that solute can't get into the cells. So there's lots of stuff that can't get into cells, and there's lots of stuff that can't get out of cells. So water then allows it, or whatever can't be dissolved in body, to pass through your body. Yeah, we're going to talk about that in a little bit. And so osmosis, water moves because most solutes can't pass through the cell membrane. Most can't get in, most can't get out. I did a little diagram of this here. Imagine that this line here, this gray line, is a cell membrane. Okay, instead of showing you a full cell, I'm just showing you a little bit of the membrane. Okay, imagine the gray thing is a cell membrane. Okay, solute, in this case, it's a little purple circles. A solute can't get out because it cannot pass through the membrane. It can't pass through. It just can't pass through. Maybe it's too big. Maybe the membrane doesn't like it. Whatever, it doesn't matter. It can't get through. Okay? Water, on the other hand, can pass through. Water can pass through in two ways. Water can pass right through the membrane, or there are also special channels in the membrane just for water, and they're called aquaporins. Aquaporins are special tunnels or channels that water can pass through. So there are two important ways that water can get into cells. Water can pass right through the membrane, or for an even faster, more efficient method, it can pass through the aquaporins. Most solutes can't get out, most solutes can't get in, but water can do back and forth through the membrane or through aquaporins. Now, if you ever learned about osmosis, if you ever try to learn about osmosis, because most people who learn about osmosis don't really learn it, because it's just like textbooks are really bad and professors are often really bad. They never actually learn it. But a term, if you've ever tried to learn osmosis, you probably heard is semipermeable. And a semipermeable membrane refers to a membrane where some things can get through and others can't. And that's exactly what a cell membrane is, because some things can get through, but others can't. Water can get through. Some types of solute can get through, but others can't get through. So we could describe the cell membrane as semipermeable. Some things can get through, but others cannot. Now that we've talked about this a little more, let's review the example that we gave earlier, and I think it's going to make a little more sense. Okay, here we have a picture of a cell. The cell membrane is semipermeable. Only some things can pass through, and in this case, the solute can't pass through the membrane. Water can, but the solute can't. So remember, when we think about this, we think about osmosis happens with a semipermeable membrane. Osmosis happens because the solute wants to come out, but it can't because it can't pass through the membrane. So instead, water moves the other way. Solute wants to go out, but it can't pass through the membrane. So water, which can pass through the membrane, goes in. Another way that you can think about this is that solute pulls water towards it. Sometimes I think about it like that. Solute pulls water. Pulls water. That's a way you can think about osmosis, that it pulls water towards it. Okay? Let's look at this example again. We have a semipermeable membrane. The solute can't pass through, but the water can. So, solute wants to go from here, from high to low, but it can't because it can't pass through the semipermeable membrane. Solute wants to go in, so instead water comes out. Water goes in the opposite direction. Again, you can think we have high solute concentration outside. We have low solute concentration inside. You can think of the water as being pulled by the higher solute concentration. Okay? So, that is what's going on here. Now, let's think about what happens with water and cells and movement in osmosis. Here I have a picture of a red blood cell. And you can see that there are little white dots, and those white dots represent a solute that, as you can see up here, can't pass through the cell membrane. Okay, so let's look at this. Outside, we have let me make this marker a little bit thinner. Outside, we have a low solute concentration. Inside the cell, we have a high solute concentration. Okay. The solute can't pass through the cell membrane. The solute can't get out. So when solute can't get out, water is pulled towards the solute. Or you can think about it this way. You can think that the solute wants to go in this direction. It wants to go out, but it can't. So water goes in. Solute wants to get out, it can't, so water goes in. Or you can think about the water is pulled towards the higher solute concentration. And what's going to happen is all that water is going to move in, and the cell is going to expand. When you put a cell like this in a situation where there's a very low concentration of solute outside, water is going to be drawn into the cell, and it's going to expand, and it might even burst. Let's look at this situation. Here we have outside the cell, we have a high concentration of solute. Inside the cell, we have a low concentration of solute. What's going to happen? Well, this again is a solute that can't pass through the cell membrane. When solute can't pass through the cell membrane, osmosis happens. And in osmosis, water is drawn towards high solute concentrations. Water is going to come out of the cell. It's going to be drawn towards high solute concentrations. And the cell will shrink because the water was drawn out by high solute concentrations. Okay. Now, the last thing that we have to do is we have to talk about how osmosis is really diffusion of water. Because I've been using these terms of like, well, in osmosis, water moves the other way that solute wants to move, right? Or I've been like, well, in osmosis, a high solute concentration pulls water or it draws water. But it's like that's not really what we learned about as diffusion. We learned about diffusion as things moving from a high concentration to a low concentration. So the question is like, can we frame diffusion in that way? We're going to talk about this for a minute here. So far, we've been saying that in osmosis, solute can't pass through the semipermeable membrane, so water moves the other way. Or another way we can say it is water is pulled towards solute. We've looked at those two examples. But here's the way that the TEAS is going to be talking about osmosis. They're going to say osmosis is diffusion of water from a high water concentration to a low water concentration. And what I'm going to do in the next few slides is I'm going to show you how osmosis is really diffusion of water. Okay? Stick with me for a minute. This is all going to make sense. Here we have an example of a cell. Okay? Look at this cell. We have a high solute concentration outside and we have a low solute concentration inside. Let's think about the concentration of solute and water inside and outside the cell. Okay, here we have, on the right-hand side, we have the inside of the cell. And over here on the left, we have the outside of the cell. Okay. Now, on the inside of the cell, we have low amount of solute, low solute concentration. On the outside of the cell, we have a high amount of solute. But what about the solvent? What about the water? How much of that do we have? Compare the inside with the outside. You can just look at these diagrams. Like, how much blue is there? Compare the two. Where do we have a higher water concentration? And where do we have a lower concentration? Where is there more blue? Where is there less blue? Look at this. Look at all that blue there. Look over here. Look at all this blue. Most of that is blue, which means that we have a high water concentration over here. Look over here. Not that much blue. That means we have a low water concentration. And so which direction is the water going to move? It is going to move from high to low, and it is going to leave the cell. From high water concentration to low water concentration. And that is osmosis. All right, we're going to do another example like this. But this is the point. If you have a low solute concentration, you have a high water concentration. If you have a high solute concentration, you have a low water concentration. And the water is going to want to move from high to low. Let's look at this here, okay? Let's do it again. Outside the cell, inside the cell. Okay, outside here, we have low solute concentration. Here, inside, we have high solute concentration. Now, what about the water concentration? On the outside of the cell, over here, outside of the cell, high water concentration or low? This is going to be high water concentration because just look at all this blue. Look at all this blue. There is a lot of water there. How about over here? There is far less blue. There's far less water. So we have a low water concentration. In which direction is the water going to want to move? It's going to want to move to an area of high to low. High water concentration to low water concentration. From high water concentration to low water concentration. So this is how we can say that water moves in osmosis. We can say from one perspective, we can say that it's pulled towards higher solute concentration. Or we can flip the lens a little bit and say that it is moving from a high water concentration to a low water concentration. So this is diffusion of water. It is moving from high water concentration to low water concentration. And that means that if you have a high solute concentration, you're going to have a low water concentration. If you have a low solute concentration, you're going to have a high water concentration. As I said here, osmosis is just diffusion of water. Like all diffusion, it is passive transport and it does not need extra energy. So here, as you can see in this diagram, where we have a low solute concentration, we have a high water concentration. Where we have a high solute concentration, we have a low water concentration. And water here wants to move from high concentration to low concentration. To look at this again, with our red blood cell example, we have water moving from high concentration to low concentration. Look at this. Inside the cell, we have high solute. That means we have low water. Outside the cell, we have low solute, which means we have high water. Which way is water going to move? It's going to move into the cell. Boom, boom, boom. High to low. Let's look over here. Outside the cell, high solute, low, which means that we have low water. Inside the cell, low solute, which means we have high water. How does water move in osmosis? It moves from high to low. It's going to move out of the cell. That is why the cell shrinks. Because osmosis is water moving from high to low. Let's look at two examples of how this happens in nature. Okay? Plants can pull in water through their roots using osmosis without, there's a typo here on my slide, and that's actually the important thing, without using any extra energy. Water moves from the dirt into plant roots without any extra energy. And here's why. This is a diagram of a plant, and then we zoom in on the roots, and then we zoom in on the cells in the roots. Okay. And then over here, we have some dirt. Okay. Now, the reason why water moves into plant roots, it sort of gets sucked into the plant roots, is because of osmosis. There are two ways to think about it. Inside root cells, there is a high solute concentration, and I did a drawing of it for you right there. Okay. Inside the dirt, there's typically a low solute concentration. So one way that you can think about this is that water is getting pulled towards an area of higher solute concentration, right? That's one way you can think about it. Water is getting pulled towards an area of higher solute concentration. Higher solute concentration is pulling in water. Another way you can think about it is you can think about it in terms of water concentration. You can say if you have a high solute concentration, you must have a low water concentration. If you have a low solute concentration, you must have a high water concentration. And that means that water is going to move from high to low. It's going to move from the dirt into the cells, from the dirt into the cells, from high water concentration to low water concentration. So it gets pulled into the cells. You can think about it in two ways. The high solute concentration inside the cells, you can think of it as pulling or drawing the water, or you can think about it in terms of water concentration, going from high to low. Here's another example. Kidneys, after they've done a lot of their filtration, they reabsorb the water into the blood using osmosis without using any extra energy. Water flows from the tubule, which is this area here. It's just drawn here in orange, from the tubule into the blood. Okay? Now, water moves from water moves back into the blood. Two ways you can think about it. Inside the blood, there is a high solute concentration. Inside the tubule, there is a low solute concentration. So one way you can think about it is you can think about the blood with a high solute concentration is pulling that water, because you can think water is drawn towards higher solute concentration. Okay? You can think about it like that. Water is drawn in osmosis towards higher solute concentration. Or you can think about this in terms of water concentration. Now, water concentration is going to be the opposite of the solute concentration. So if the blood has a high solute concentration, it has a low water concentration. They're flipped. If the tubule has low solute concentration, it has high water concentration. So that means that the water moves from the tubule to the blood, from high to low. Again, you can think about it two ways. You can think about the blood with a high solute concentration in osmosis pulls water towards it. Water is drawn towards higher solute concentration. Or you can figure out what the water concentrations are, and you can think about water moving from high concentration to low concentration. Okay? And that water concentration is going to be the opposite of the solute concentration. And there you go. Now, two more things to talk about. We're almost done. We have been giving examples of water flowing in and out of cells and stuff like that. Sometimes people ask, what do you call it? Is there a special word for when the solute concentration is the same inside and outside a cell? And yes, there is. And you call this isotonic. Very important. Isotonic. Solute Same concentration inside and outside cells. Isotonic. And isotonic also opens the door to talking about some other words that use tonic. We can describe high amounts of solute or low amounts of solute in terms of these words tonic, using tonic. And so if you have very low, if you have very high solute in the solution, you would call that a hypertonic solution. That means that there is more solute in this, I'm sorry, a hypertonic solution means that there is a very high amount of solute relative to the cell, and a hypotonic solution means that there is very little solute relative to the cell. In the situation where the cell is in a solution that has about the same amount of solute, we call that isotonic. So, isotonic. There you go. Okay. So, here we can do a couple quick examples here. The solution outside the cell is hypotonic. How is the water going to move? So, if the solution outside, we can think through it. If the solution outside is hypotonic, that means we have low solute outside, and that means we have high solute inside. Okay? How will water move? We can think about it this way. We can think that water is drawn towards high solute. So we can say, oh, it goes like this. It's drawn towards high solute. Or we can say that there is a high water concentration outside. There is a low concentration inside, and water is drawn from high to low. Same thing here. Solution outside of the cell is hypertonic. What's that going to mean? High solute concentration outside, low solute concentration inside. Well, one thing that we could think of is we could think that, well, water is drawn towards higher solute concentrations. Water goes out that way. Or we can reframe this in terms of the water concentration. We can say, well, a low solute concentration means a high water concentration. A high solute concentration means a low water concentration. And similarly, water moves from high to low. And if we have isotonic, it means we have the same in and out, and water will move in, it will move out, but it's not going to move more in one direction than the other. So that's it. That is our video on diffusion and osmosis. I'm going to do a quick review. If you got any questions, put them in the chat. And then tomorrow, the day after, sometime soon, we'll do a whole bunch of practice problems for this stuff. Any questions about this before I do the review? Feel free to add them right now. Throw them on in. I'll start going. If you have any questions, we can talk about that in a sec. So diffusion is when a substance moves or spreads from a high concentration to a low concentration. We saw this with a guy smoking as the smoke spreads out. We saw this with food coloring spreading out in a glass or a beaker. Things will do this on their own. It does not need outside energy. Diffusion from high to low concentration happens in many places in our body. Some examples that you probably know about are oxygen and carbon dioxide moving from high concentration to low concentration in the lungs. And this is an example of passive transport. It happens on its own and does not need any outside energy. Substances can move sometimes through the membrane of cells. And in that situation, these substances move from high concentration to low concentration. They can do that if they can move through the cell membrane. Sometimes they can't move through the cell membrane, but they can move through these little channels or tunnels. We call that facilitated diffusion. It's still diffusion. It's just movement through these channels. It still doesn't require energy because we're moving from high to low. Okay. But something that does require energy is when we pump in the opposite direction. Right here we have high inside the cell, we have low outside. The natural, passive, non-energy using way would be from high to low. But if we want to go from low to high, that is going to require energy, and we call that active transport. Another example here, high concentration out here, low concentration in here. This way, low to high would be passive, no energy. But if we want to go in the other direction, from low to high, that is going to require energy, and it's going to be active. Oh no, active. Okay, active transport. Now, as we said, most solutes actually can't pass through the cell membrane. The examples that we looked at were kind of special examples. Water can pass through the cell membrane, though. It can pass through on its own. It can pass through in aquaporins, which are special tunnels or channels. And osmosis happens with a semipermeable membrane. You can think of osmosis in two ways. You can think of water is drawn towards high solute concentration. Here it is. Here's high solute. Here is low solute. You can think of water being drawn towards high solute concentration, or you can also think about this. Oh no. Let's see. Sorry about that. Or you can also think about this in terms of water concentration. That if we have a low solute concentration, we have a high water concentration. If we have a high solute concentration, we have a low water concentration, and water moves from high to low. Same thing here. High solute, low water, low solute inside, high water, water moves from high to low. It's going to move inside. Oh no, 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 no. Water moves from high concentration to low concentration. It's going to move out of the cell. And lastly, in roots and in kidneys, water moves via osmosis. In this case, it moves out of dirt into the cells. You can think about it moving out of the dirt into the cells because it is drawn in, it is pulled in by the high solute concentration. Or you can think of it as moving from high water concentration to low water concentration. Similarly here, water moves from the tubule to the blood. You can think about it as being drawn by high solute concentration, or you can think of this as high water inside the tubule and low water in the blood, and it moves from high to low. Two different ways to think about it. You will probably see both of these ways of talking about osmosis on the TEAS. You can think about it being drawn in by high solute concentration, or you can think about it moving passively from high to low. And since it's a form of diffusion, osmosis does not require energy. Okay. And then lastly, we talked about hypertonic, which means a lot of solute, hypotonic, which means very little solute, and isotonic, which means the same amount of solute. Okay. To finish it up, let's look at these two examples that we did at the beginning that maybe some of you got wrong. Okay. Which of the following is true of passive transport? Well, if you're learning this for the first time, now you know what passive transport is. And passive transport means that it happens on its own, does not require energy. Does not need energy. And passive transport is going to be a situation where we go from high to low. Okay, so let's go step by step and see what we can eliminate. A, it is movement of a substance from an area of low concentration to an area of high concentration. No, that's not true. Passive transport is high to low. If you want to go from low to high, you need energy for that. Cross it off. B, it is a process that typically requires energy. No. Passive does not need energy. Active needs energy. So we can cross off B right away. C, it involves a chemical change that makes a substance more soluble. Now, something that I always say for the T's is, do you know this for sure? Because you might see C and you're like, I don't know. I don't remember learning that chemical change. Maybe it's just soluble. Then maybe, no. Did you learn that? Did I say like, oh, this is like very important to remember that passive transport involves a chemical change? No, I never said any of that. So don't choose it. Okay. I'm not going to eliminate it right away because maybe D is a really bad answer and we'll have to choose C, but don't pick something that you don't know. D, it can involve either solutes or solvent. Okay, think about this. Passive transport. Well, solute, as you know, can move from high to low. Salt, sugar, things like that can do passive transport from high to low. Oxygen, carbon dioxide can do passive transport. Those are solutes. They're dissolved. What about solvent? Solvent is something that does the dissolving. So solute is water. Okay, well, solvent, such as water, can water move from high to low? Absolutely. When solvent moves from high to low, it's osmosis. When water moves from high to low, it's passive transport. It's osmosis. So there we go. D. D is correct. C is total garbage. Solute or solvent can do passive transport because osmosis is passive transport. Lastly, what is a correct description of how osmosis functions during water reabsorption in the kidney? Tease loves questions like this. Let's go step by step. A, energy is expended to pump water back into the blood from the tubule. Okay, no. We know this is wrong because we're talking about osmosis. Osmosis is a type of diffusion. Osmosis is diffusion of water. Diffusion of water. Diffusion is passive. Diffusion happens on its own. So energy, no. If osmosis is happening, you do not need energy for it. Cross it off. Energy, no. Diffusion happens on its own. Osmosis happens on its own. B, water moves from the tubules high solute concentration to the blood, low solute concentration. Now, this is one of the ways that TEAS is tricky here. You got to remember, are you talking about solute or are you just talking about solvent, right? If we're talking about solute, water is pulled towards a higher solute concentration. So water, if it's osmosis, water is not going to move from a high solute concentration to a low solute concentration. In osmosis, if we're thinking about it from the point of view of solute, water is pulled towards higher solute. So B is wrong. C, water moves from the tubules, high water concentration to the blood, low water concentration. Ooh, that sounds pretty good. Osmosis is water moving, water diffusing from high water concentration to low concentration. So I'm pretty sure C is right. Let's take a look at D. Water moves against its concentration gradient as it moves from tubules to the blood. Now, against the concentration gradient means you're pushing it in a way that it doesn't want to go. To get something to move against its concentration gradient has to be active. It needs energy. And osmosis is not an active process. Osmosis is a passive process. It is not against the concentration gradient. So get rid of D, and we are going to choose C, and that is our correct answer. So I hope that if you were a little shaky on those questions to begin with, I hope it's clearer now. And we'll have even more chance to practice when we talk about this stuff coming soon. We're going to look at must-know questions on diffusion, osmosis, and transport. We'll look at the kind of questions that you'd see on life science, chemistry, in anatomy and physiology. We'll do, I don't know, 20 of them, maybe 15 of them, so that you can really be prepared for all the different ways that the TEAS is going to ask this. So, as I always say, if you have questions, send me an email, tyler@teasandoneday.com. I love hearing from you. I love hearing your questions. I love hearing your compliments, your just whatever whatever you want to throw at me. And if you like how I teach, you can check out teasandoneday.com. I have a full TEAS chemistry course, teach you all the most important stuff for the TEAS. People tell me they really like it. So listen, we're almost at 3 Central for me. Any questions as we wrap up? If you have any questions that I can help you with, let me know right now. I'm happy to answer any questions. If you want to know when my live streams are, make sure you sign up on my website so you can get my email. I'll let you know. If this was helpful, let me know. If this was not helpful, let me know. It's not going to hurt my feelings. You can be like, this was like the worst lesson I've ever seen. I'm more confused on osmosis than I was when I started. It's not going to hurt my feelings. I want to get your feedback so that, I can make it better. Anyway, let me know if you have any questions. Do I have a TEAS? Do I have a full TEAS prep course? Not yet. I'm making one. And here's a problem. I'll just be blunt. I'll be blunt and honest. Quality takes time. It takes time to teach material in a way that people can learn from. Like that's my belief. That's like my religion. And there are plenty of people who disagree with me. There are plenty of YouTubers out there, and there are plenty of people writing, books and stuff like that. But I just think that to make good content that helps people, it takes time. And I can't rush it. I'm trying to make videos like as quickly as I can. I'm doing live streams. I'm trying to like help people with this stuff. I can't wait until I have a full TEAS prep course. It just like it takes time to like really teach you stuff. I mean, like for example, today we spent like 2 hours on diffusion and osmosis. And I hope that by the end of this, like it was really making sense to people, right? But it took 2 hours, right? There are like plenty of TEAS videos that are like 5 minutes on diffusion osmosis. And if you don't already understand diffusion and osmosis, like that 5-minute TEAS video isn't going to help you. And I know there are lots of books and videos out there that are charging you money to give you a 5-minute diffusion and osmosis video. And it's just like, I can't like do that. I can't like do that in good conscience. I can't sell somebody a 5-minute or a 10-minute video that I just know in my heart like isn't really going to help them. So yeah, so I would love to have a full course. I'm working on it. Like, trust me, I'm like working on it. You can always like, if you have questions, just send me an email, right? If you're like, oh, I really like have a question about whatever, just like send me an email. Maybe we can do like a live stream on the topic that you want, right? If it's something that you're like from math or from reading that's like really frustrating you, send me an email and maybe you can get a bunch of your friends together and we'll like just do a live stream on that, even if I don't have like the whole thing yet. But I don't feel right about live streaming or selling something that I just don't think in my heart is going to help people. Okay. Yeah. You're right about the ATI. Oh, the ATI book is just garbage. It is so bad. I just can't believe how those ATI people write that book. That there's, as I always say, there's so much on the test that is not in the ATI book. There's so much in the ATI book that is not on the test. It's like they're from two completely different universes. And those ATI people make the freaking test. It's like, how can there be such a wild difference between what's in the book and what's on the test? It's just like, I I cannot like wrap my head around how awful that is and how hard it is and like how unfair it is for people who are busting their butts trying to study and ATI doesn't even tell you what's going to be on the exam. Oh, it just drives me crazy. To answer your question, um I have done as much research on the teas as absolutely possible. I have tried to study the teas as much as it is absolutely possible to do so. So I have looked at hundreds and probably thousands of teas questions, and I really have learned a lot about the teas. Any other questions before we wrap up? Well, it's always a pleasure to do these live streams. I have so much fun when I do these live streams, and let me know if I can help you in any way. Send me email, and I look forward to talking to you. And I will let you know when we're going to do this live stream about the must know questions. All right, send me email if I can help. Check out my website, teaseinoneday.com. I will talk to you later. As I always say, like, best of luck on the teas. I hope you crush it. I hate this test so much. I hope that I can teach you all to crush it. All right. Thanks a lot. See you later.